And then tonight we have our guest speaker, Dr. Oren Eliezer, 4X6LF. And I want to hand it over to Keith. And Keith, I'll quit sharing here. And I'll let you go ahead and introduce Oren. Keith is a member of our club, AK0Q, and he is very involved working with the ES100 chip that we're going to be talking about tonight. And he's got some really neat, even has some great work put up on the Universal Solder website for the company about using the ES100 chip. So really, really good stuff. Keith, go ahead and take over.
Well, good evening, and thank you, Kevin and Dave. It's great to be here, and thank you, Oren, for being here as well.
Sure.
I just want you to know I first had contact with Oren in 2018, and right now is the first time I've ever actually seen him. So I had heard about the Everset 100 WWV receiver and wanted to build one, and I needed some help. And he helped me get it going, and it's been a successful project, working with the ES100 and then partnering it with an Arduino. So I found it fascinating then. I find it fascinating now, and I think it will be for quite a while.
Mm-hmm.
Dr. Eliezer has a PhD from the University of Texas in Dallas. You can read the bio for the greater details on that. He has authored or co-authored over 60 journal articles, which in higher ed is pretty darn good, and 60 invited talks. He's worked entrepreneurial companies and major manufacturers, and as you said, he has the call sign 4X6LF, which suggests it is low frequency. So I'm delighted to welcome Dr. Oren Eliezer. And take it away, Oren.
Thank you very much. Thank you very much for the great introduction. Can you all see my screen? You do? Okay, thank you. So I'm glad that this works. I put together slides from various presentations that I've made in the past and added some and edited some, and there's just so much information that it probably won't fit into one meeting, but maybe we'll talk about it again in next month's meeting, depending on the level of interest and comments from the audience. So let's get this started. My call sign back from 3 decades ago from Israel is 4X6LF. And when I got it at the time, I was like, oh, why LF? I'm more of a VHF, UHF guy, hardly even HF. My father was an officer on ships, so he was not only a radio amateur, but actually dealt with that professionally for a while. And so very much an HF operator. And growing up in Israel in the 70s and 80s, we used to use HF extensively for a phone patch, because in those days, an international call to relatives back in the US would be kind of ridiculous. But myself, as an amateur, I mostly dealt with VHF and UHF. But I guess my call sign from like 1990 or so predicted that one day I'll be working in LF. So here's my work in LF. It's been a lot of fun. Really enjoyed that project. From a business point of view, the company was not very successful, and I'll talk about that too. But it was definitely very enjoyable to work on this project at the time. It started in about 2010. These are some pictures that I took at the station, and I'll go also through some pictures during my presentation. We see an expert by the name of Paul, I think, looking at that coil for impedance matching at the helix, at the interface to the antenna. On the right side, I put a link to the information that I put on the Google Drive, all kinds of interesting files and publications, and so you might find that interesting. In fact, if you aimed your phone at that QR code, it would directly take you to that Google Drive, and you'll be able to download things from there. And feel free to connect with me on LinkedIn. I'm easy to find. It's a Hebrew name that's not that common, Oren Eliezer. So you just type it into LinkedIn, find me, and I'll be glad to connect with you. Okay, let's get this started. It's not moving to the next slide. Okay, let me figure that out. Maybe because I'm sharing the screen. It's still stuck on the first slide, right?
Yes.
Wait. I see where I should be. I should be here. Now it moved, right?
There we go. Yeah.
Okay. So I'll be talking about the history and background for the broadcast enhancement, which I was involved in starting 2010. The new broadcast format, a lot of details to share, and some communication theory, which I hope you can follow. I'll show the new time code generator that we had delivered to NIST at the time, which they were very happy with, replacing their old one from the 1970s. I'll be talking about the receiver chip designed for the new broadcast and products that are based on it, which are mostly this single analog clock from La Crosse. Unfortunately, no digital products available, although I have a prototype here that never went into production. This you see it on the camera. And there are the modules that Universal Solder is offering. I used to have a bunch of them at home, and hobbyists contacted me, and I packed them in a box and shipped it to them at my own expense. Didn't even charge them for the delivery till I found a Universal Solder, and they were willing to do that. So I just sent everything to them, and that's where you could get those modules these days. Okay, so you probably already know of these other popular LF-based timecode broadcasts worldwide, in addition to the 60 kilohertz WWVB broadcast, and that is MSF from the UK, DCF77 from Germany, actually quite popular. Many people use it, and JJY in Japan. And I wanted to talk about the Japanese one in particular because they have two stations, something that was also considered here in the US because of the shape of Japan being kind of elongated, and they didn't want to waste energy and just, blast from some central location and mostly go into the ocean. So they placed one in the north, one in the south. And of course, there'd be places in the middle that may receive the two at the same level. So they couldn't be at the same frequency. And so they had to have two different frequencies, which meant that the clocks in Japan have to be able to support both frequencies. So they have two crystals, and the clock has to first look at one frequency and then the other, because what if you move one day from one city to another city and you have to receive the other one? And they don't even have daylight saving time to worry about, that adjustment of 1 hour twice a year. And still, 70%, this is some statistics that I heard years ago, 70% of clocks in Japan are radio controlled. They care about punctuality. And here in the US, people buy any piece of crap in Walmart that they have to keep resetting, not just twice a year for daylight saving time transitions, but just, the ongoing drift. So that's one of the reasons people don't really care much about WWVB, I'm afraid, other than people like us. Although you could read on Amazon some good reviews for those who do appreciate a clock that actually works and they never have to set. So the WWVB station has 70 kilowatt of effective radiated power. It's in Fort Collins, Colorado, as you all know. So that's not exactly in the center of the continental US. So the East Coast suffers a bit when compared to the West Coast. But hey, what about Alaska and Hawaii? They're to the west, so maybe it makes sense to not be exactly centered. And Alaska, as you can see here, is even outside of that outer circle of 3,500 kilometers, and so is Hawaii. And maybe they weren't even intended to be well covered, nor were they with the legacy broadcast, but they sure are now. That's a photo that I took at the station when I visited with my son in 2013. I've since been there several times, including with my fifth son. And I'll show you a photo about Hawaii soon. So here is a simulation of the coverage where Hawaii may appear to be somewhat marginal, and so is Alaska in red. Each color represents a drop of 10 dB or an order of magnitude in the field intensity, in the signal strength of the received signal. This simulation was done by Peter Hansen from SPAWAR. Just yesterday, coincidentally, I attended a local talk here by the IEEE. The presenter, she was Carrie Moran from SPAWAR. And so it was about PNT, and I mentioned Peter. So he apparently retired in 2013 after 43 years in the Navy. But he was able to run these simulations, which were very helpful. So for any given time of day, he could give us the anticipated signal strength worldwide. And apparently with 100 microvolts per meter, even the legacy clocks can work if they're outdoors and not suffering from shielding losses of the building, and I will discuss that, or man-made noise, which is actually the dominant obstacle. So here I'm listing those obstacles to proper reception. So first of all, the propagation conditions change over a day, and you understand that very well as amateurs, with the night being more favorable because of how the ionosphere is used to reflect the signal back. So we see these two different pictures. On the right is the night time. The time is specified in UTC, but it is actually night on the right, and we see how far the signal can reach. And on the left during the daytime. So the red areas represent that signal level that is useful. Now, the shielding losses that I speak of in the second bullet are a result of the use of materials like cement with reinforced concrete, not wooden shacks. Of course, they're kind of transparent. But large office buildings and hotels, hospitals, things like that are based on those kind of materials. And so reception inside of them is particularly challenging. And I did measure as much as 30 dB losses. I will show on my next slide one particular example. Antenna orientation is another thing. As radio amateurs, you are well aware of where you're receiving a signal from. And I remember back at our station at home that my father operated, we had a motor and we can rotate our Yagi antenna. Well, in these consumer products, I'm showing this clock now, people just place it randomly, right? Or they hang it on whichever wall they want to be able to observe the time. And the antenna inside would not necessarily have the correct orientation. And I have a whole discussion about that we may or may not reach today. And then, as I pointed out before, there's a very dominant source of an obstacle, and that is interference, or EMI, coming from electronic devices, screens, chargers of cell phones, appliances. It just is, it's much noisier than it was decades ago when the broadcast first started. So regardless of the signal level at which the WWV broadcast may be received at, you really need to care about the level of interference accompanying it. And then on the East Coast, there's also on-frequency interference from MSF in the UK operating at exactly 60 kilohertz. And when the propagation conditions are favorable from there, and your antenna orientation happens to be more towards UK than towards Colorado, then that's actually a significant factor. And I studied the statistics of that. So here's an example of a spectrum analyzer shot that I took from the offices of Extendwave years ago, where you can see the WWVB signal received on the top at some reasonable level because it's near the window. And near the window, you don't quite suffer the shielding effect that you suffer deeper inside the building. And then inside the building, on the bottom, with all those red labels, you see the signal as much as 20 dB lower, 2 orders of magnitude. And I didn't go very deep in, like few meters from the window. You also see all these other signals popping up that represent interference from other devices that are in the vicinity. So overall, very challenging environment. And I say this because prior to my work at this frequency, I did a lot of work in millimeter wave, both in the Israeli military and Texas Instruments. I worked on cellular. And usually, I'd be operating in a band that would be somewhat protected, even if it's the ISM band. You could have microwave ovens there, but communication equipment would have reasonable signal levels, would adhere to FCC regulatory limits. Here, no such protection. So any level of junk can be experienced. So here's that photo from Hawaii that I had promised. I was just there with my wife and returned just like a week ago. And you see a photo that I took of this very clock receiving the time there successfully. So this clock is based on the ES100. Too bad it's not, for sale. It's just one of the prototypes I got from the company in China that designed it based on our chip. And so you see a booklet that was in the hotel in Ohio, and you see the view that I had from the window. I always like to carry that with me and receive the signal at very distant places, one of which was south of Brazil, Porto Alegre, where I went for a conference in 2014. So not something that you could easily do with the legacy receivers.
And okay, don't forget, I got it from Greenland.
Oh, right. I heard that in South Africa. that's a big one. I gave it to somebody not in Johannesburg, though, where the level of MMN is high, but he went on some safari trip with my prototype receiver and was able to receive the signal there. And UK while MSF was off. One good thing about MSF is there are lots of outages, and those can be used as opportunities to receive WWVB all the way on the other side of the Atlantic. But generally speaking, going to east-west is difficult, as I point out in the second bullet below this, whereas going south, because they share nighttime with us, is easier. So it's not just the distance, but also the time zone that matters because of these properties of the atmosphere. Okay, so the enhancement. First of all, the time code was introduced on WWVB in 1965 when the station transmitted at 5 kilowatt of power, and the mindset was envelope detectors and simple receivers. It's 1965 after all, and I'll go into detail and explain what I mean by the 1965 mindset, because very inefficient overall. The ERP was raised to 7 kilowatt, then to 13, and in 1999 to 50 kilowatts. And then with the two antennas there, by 2005, they were able to reach a total of 70 kilowatts of ERP. So effective radiated power includes the antenna gain. But in 2009, realizing that even that is not enough, and going much higher than that is kind of ridiculous, it was actually considered. So when I was first time at the station, Paul was there too. That's that picture here at the very beginning. You see him in the middle photo on the bottom. And one of the things that he, as an expert in high power, was looking into was the possibility of upgrading to even higher power of transmission. And one of the conclusions was that it wouldn't be easily possible because even the isolation there would have to be upgraded to deal with higher voltages. So not so easy. It wasn't just a matter of boosting up the power from the amplifier, having a stronger amplifier, but also the antenna would have needed changes. And it doesn't make sense to just brute force it. And the enhanced broadcast that I will be speaking of is all about a different modulation scheme and data represented differently, and I'll get into those details. But it's interesting that another potential solution that was considered was a second broadcast station similar to what is available in Japan, possibly also at 40 kilohertz as in Japan. And of course, that would have been a huge expense. Just imagine a second station with staff and things like that. So it's good that was abandoned because not really needed or justified. Finally, in 2010, NIST published a Small Business Innovative Research solicitation. So government agencies, including NIST, the DoD does this a lot, are obliged to use a certain portion of their budget to be spent on research conducted in small businesses. Small businesses are up to 500 people, US-based, to stimulate the economy. At the time, there were even more such grants that were being given because of the downturn. But the NIST SBIRs were only 90K, smaller than those of the NSF and others. And so my friend, Professor Walid Halil, I'll be mentioning him on this slide from the Ohio State University, noticed this solicitation and alerted me to that and said, hey, look at this. This is something that we could do together, the Ohio State University, in collaboration with your startup. And let's write a proposal. Okay, when is the deadline? In 5 days. Oh, that's not good. You should have noticed this months ago. So we scrambled and quickly put together the proposal, working kind of day and night. And they liked our proposal. It was chosen out of 10 other proposals. And so we won the 90K amount. It doesn't go very far, but we were able to show some proof of concept based on simulations and analysis. And after the 6 months of the phase one, we were granted the phase two, which is $300,000. Also not quite enough to design a chip, which required private investment in the company. Eventually, the company, that business of the company was spun out of Extendwave and called Everset Technologies. Everset, a name that the CEO came up with because the clocks are always set. Very problematic name, though. Anytime you put Everset in Google to search for something, it corrects it to Everest. It's just too similar in spelling, and they assume that it's a typo. So not Not a good name. Similar problem with Universal Solder. It's going to correct it to Universal Soldier, a well-known movie. So one has to keep these things in mind when naming. So at The Ohio State University, I visited their anechoic chamber, just a fun place that I thought you guys would like. So I included the photo of that. The electroscience laboratory, as it's called in The Ohio State University, is well known for their antenna development capabilities. They collaborate a lot with the Air Force. There's that Air Force Base in Dayton. And so, yeah, it was fun to work with them. But on the communication theory aspects of the broadcast format, and that was the majority of the work on this project, I collaborated with the local university in Dallas, the Southern Methodist University, and had a PhD student from there. Her name was Yingxi Liang from China, worked on that. So the broadcast format was developed to a great extent by myself and a Chinese student. And no other companies were involved. And of course, NIST gave their blessing and had to approve the details. But to me, that was something kind of unusual because I was involved in the development of Bluetooth on behalf of Texas Instruments. And I was involved in IEEE committees, and in both Bluetooth, which was not IEEE, and IEEE committees, there's always the politics. You suggest something, somebody suggests something else, and they don't want your IP to go into the standard. So there's a fight even over the best ideas, which should have been, accepted immediately. And here, I got to define a whole broadcast format on my own without anybody arguing it, and we got to patent it. Anyway, I'll get to those details. So the legacy broadcast was out since 1965, operating at 70 kilowatts. I mentioned this already, but the modulation being AM pulse width, not very robust, and the encoding being just BCD. And I'll go into the details of the more sophisticated encoding used by the enhanced broadcast. So here is that beast of 50 kilowatt that I photographed at the station. And so there are multiple such amplifiers there that is used to broadcast the signal. And here is that impedance matching coil that I showed you on the first slide. Very, very large for the impedance matching between the output of the power amplifier and the antenna. This is what the old time code generator looked like from the 70s, and has these manual controls on it, not very automated. In fact, someone from the station had to be there on the weekend of DST, daylight saving time transition, in order to flip the switch. And I heard of at least one case when there was a snowstorm and couldn't make it to the station. So the station is left unmanned just with alarms over the weekend. And this flipping of the switch really created a problem that the new TCG solved. Of course, it wasn't its purpose. Its purpose was, primarily to produce the new broadcast format with phase modulation. But an important addition was also the automation of other features, which the staff there greatly appreciated. It can support remote control via Ethernet, but that's not used and considered somewhat risky. And it's configurable. Everything is like software based, and there's an FPGA in there. So even the hardware things are somewhat configurable, but it hasn't yet been modified since the installation there in 2012. So it's been 14 years now. And as far as I know, no major failures in the timecode generators. Only 8 were produced, and Extendwave no longer exists or ever set. So there won't be any more than 8 produced, but all the documentation is there, and the station has most of those 8, and hopefully they'll be able to cannibalize parts from one or the other. But as I pointed out, it's been some years and it hasn't failed yet. So hopefully it will go on for as long as the station needs it. And of course, the interface is more modern, being based on a touchscreen rather than those toggle switches. This is the basic waveform of a bit in the old broadcast, and then I'll show the legacy one, how the new one differs from it. What we see here is half a second of low amplitude, half a second of high amplitude, representing a logical 1, and the 0 is represented by a 0.2 second low, followed by a 0.8 second high. And so you see both of those on the left. And the mindset from the 1965 era was that, it's a simple implementation that you would need to decode this. And they didn't have the principles of digital communications in mind, with concepts such as the distance in the signal space. I'll get to that term later in my talk. The distance in the signal space between the 1 and the 0. Although this is a term coined by Shannon in 1947, but digital communications really became a thing only much later. So it's a wasteful modulation scheme. That's what I'm saying. With the 0 and 1 differing only in that 0.3 seconds. And I'll show what that looks like in the signal space. And the typical structure of legacy AM receivers, the chips, the analog chips, is as you can see in this diagram. So being based on a crystal filter of about 10 hertz bandwidth, around 60 kilohertz, they couldn't have that integrated in the chip. So after the first stage of amplification, the signal goes out of the chip, into that crystal, back into the chip. And then there's the AGC circuitry, envelope detection, all of which have relatively large time constants, with the bit rate being 1 second and the carrier being 60 kilohertz. So even slower than AM receivers, for AM broadcast stations. So those capacitors could not be integrated, and they are external. So overall, not a very integrated solution. And of course, the decoding of the ones and zeros is not part of these analog chips, and is typically done in a separate chip. Whereas the ES100 includes both the entire analog front end without the need for all these cumbersome analog passives, and the digital demodulation and decoding. So the legacy format, when I first looked at it, I thought, gee, this is kind of wasteful in a few different ways. Not only is the representation of the information not efficient, being based on BCD, binary coded decimal, with the minutes being separate, the hours being separate, the day being separate. So you see that table here. But I also identify, look at these 7 bits that I circled called the DUT, the time difference between astronomical and universal time. And then that additional bit, LY, the leap year. I mean, why do we need that? If we know the year, there's a deterministic formula, not a very simple one. It's not every 4 years that we have a leap year. Okay, every century there's an exception to that, and then every 4 centuries there's an exception to the exception. So, but it's just a few lines of code, and we implemented that. And the ES100, it's a leap year or not, and that information does not have to be in the broadcast. So, any comment on that, or just somebody coughed and wasn't muted? I thought I heard something. So the difference in universal time has to do with the astronomical time deviating somewhat from the very precise atomic time, because the Earth doesn't actually rotate at a very fixed and regulated speed. So we have about 365 days a year. It's 365 and a quarter. That means, around the sun. But do we have exactly 24 hours in one rotation? Well, no. The hour was defined based on that, but because of all kinds of phenomena, including earthquakes, this can change. Generally speaking, the Earth has been kind of slowing down, which is why we needed positive leap seconds, which meant that certain minutes had to be extended from 60 to 61 seconds. I wonder if everybody here knew that. A lot of people think that all minutes have 60 seconds in them. Well, no. The photograph shows the error that was experienced at different points in time. This photo was taken when I was at the station in 2012, but you can see the dates in that old-fashioned looking table specifying the errors that were experienced. And they required correction so as not to accumulate over time, which could have caused the sun to be down there at noon instead of up here. So the idea is to track that. And since 1972, these corrections were made 27 times, all of which were positive, meaning that minutes were extended from 60 to 61 seconds, either on June 30th or December 31st. The last one we had implemented was December 31st, 2016, which is many years ago. Typically, we needed them every few years, but that is because of a speeding effect that the Earth is experiencing due to climate change and ice melting from the poles. Interesting, right? In fact, it is predicted that by 2029, we will need a negative leap second. And when I proposed for the new broadcast format to not even support negative leap seconds, and that's how I initially defined it, luckily, Tom van Bach, who may be in the meeting right now. Tom, are you there? He was at that conference, at that meeting of PTTI, Precision Time and Time Interval, and he sat down with John Lowe from NIST and with me and said, no, the Earth can actually accelerate, will accelerate, and we need to support the possibility of a negative leap second, meaning a minute that is shortened to 59 seconds. So you can go check out his website. He does very interesting things. He's well known in the field of time. So let's look at the principles of the enhanced broadcast. So it uses phase modulation that is superimposed onto the existing modulation and supposedly not interfering with it, and I'll get into that point. A synchronization word was added, which is redundant, so it doesn't really carry information, but it's useful for tracking rather than acquisition, something that I will explain later. The information, meaning the time, the date, is represented more efficiently than in the legacy broadcast, requiring fewer bits, and then bits are added, parity bits as they're called, for error correction coding, giving it some robustness. So if an error falls in a bit, then the code can detect and correct that. Not something that most clocks out there have, based on the legacy protocol, which is why we see sometimes the wrong thing on our display. And I'll show some photographs with examples of that. An advanced notification for DST transitions was added. After all, we know in advance when DST will occur. Congress only changes that once in a few years. Last time was like 2007 or so. And so we provide the indication of when the DST transition, the next one, will happen. It's available months in advance. So if for whatever reason, on that crucial weekend when that 1 hour correction needs to happen, if reception is not working due to excessive noise or whatever, the clock will still get it right. With the older ones, the notification only came out around the time of the DST transition. So if you weren't receiving for whatever reason, your clock is going to be 1 hour off. And then 6-minute sequences were added, where the whole 6 minutes communicate just one time without even the date. So from an energy point of view, it's not 6 times more energy, but more than that, because it's only representing a time. That added robustness of over an order of magnitude. The ES100 modules do not have that mode enabled, but all the details are made available in the broadcast format document available on the NIST website. So anybody can design a receiver for that, and sometimes students kind of do that for fun. With that sequence, you could receive this, I think, in Australia, even in the presence of strong noise. Maybe I'm exaggerating about Australia, but you get my point. And then another thing that was added is messaging capabilities, although that is not in use. So the idea is that at the beginning of the frame, we announce whether it's a message frame or the time frame, and then it's populated accordingly. So here's what the waveform looks like with the phase modulation added. The first 2 bits have the phase, not inverted, and then that third bit has it inverted. So the information represented here is 001, whereas if you look at the top of this diagram, we see 101 with the historical protocol. So the two are completely detached from one another. While the AM PWM legacy protocol may be, sticking to its old representation of information, a completely new and independent set of bits is represented by these phase inversions. And while the envelope detector-based receivers of the type that I described before are not impacted by this because they only look at the envelope, some equipment that is based on phase locking was impacted, and some amateurs had such equipment and were annoyed with the fact that, hey, who's tampering with their WWVB phase of carrier, and they complained. And not only did they complain, but a certain police station that was using it for timing and others. And so for a while, I forget it was a few years, but for quite a while, NIST would turn off the phase modulation at certain intervals during the day to allow for that kind of equipment to lock. Paul, who's here in the meeting, designed a DPSK, as he called it, a circuit that would recover the phase despite these phase inversions, something that exists in every BPSK receiver because you have to do a phase recovery. But I would claim that, we really don't need these broadcasts in most settings for frequency standard. Back in the day, they provided that solution, and there's still that solution with the 10 megahertz and the other sources that NIST is broadcasting at. But nowadays, all amateurs should have very accurate crystal-based sources available to them. Back in the 80s, my father already had a Kenwood, transceiver, digital control, crystal-based. So, and there's GPS. So WWVB should not be considered a source for locking equipment when you have that already available to you from so many other sources. But anyway, it's still possible. So here's what the math tells us. Without inverting that, the one with respect to the zero, so we see that with the red and yellow, without inverting them, they are very similar to one another. How do we determine that similarity? So there's a mathematical process called the Gram-Schmidt orthogonalization process, which is intended to define a space, a signal space. Here we see it spanned by phi 1 and phi 0, in which your signals can be represented as some kind of linear combination of the basis functions. And so in the space that is shown here with phi 0 and phi 1, if the 0, which is 0.8 seconds of high power and 0.2 seconds of low power, is represented by the red dot. And the 1 is represented being 0.5 seconds low and then 0.5 seconds high is represented by the yellow dot. Notice that both the red and the yellow have similar power. The distance from the origin corresponds to their power, but they're very close to one another. And in the presence of additive noise, can be easily confused with one another. Using the same signal space to describe an inverted form of X1, X1 being the representation of the 1, that is the yellow. So the blue signal being its inverse, you see moves 180 degrees with respect to the original X1 and distancing it from the red signal considerably. And when we look at the ratios of the distance, the previous one being 0.47, the new one being 1.45, and power being square of that, we get the ratio of 11, representing more than an order of magnitude of improvement in signal to noise ratio, okay? Without doing anything to the power, just representing the signal differently. So I'll talk about that a little more later. Now let's look at how the data is represented. So we see in black the old representation that I showed before with that timing correction or timing error with 7 bits that are not really needed. You think about the amount of energy spent in sending them on a daily basis. And so all the useless portions of the information have been replaced with information that is actually useful to the clock, including a sync sequence in the beginning, which is not information, but intended only for timing. And when you think about it, most of the time, the clock doesn't need to receive information. Okay, how do we even define information? Information is something that you have no idea of and you need to be informed of. Okay, there's actually a measure of amount of information. There's a whole information theory and how to quantify the amount of information. So if somebody tells you something that you already know, there's no information that was conveyed to you. So a clock can independently keep track because we know that 8 p.m. comes after 7 p.m. We didn't need to be informed that every day. And we know that December 31st comes after December 30th, not in November, but in December, 31st after 30th. And so we really only need to keep track of our drift. That's very different. So once we've acquired the time, we put the new clock, on our desk or on the wall, we put in batteries. Once we've acquired the time, from that point onwards, we really only needed to track to compensate for drift. Occasionally, information that it may receive that is new to it is the DST schedule and leap seconds. So I'll discuss that. So notice the amount of bits dedicated to representing the time and the amount of bits represented to daylight saving time. So daylight saving time actually had very few bits dedicated to it in the old legacy protocol. You see bits 57 and 58, and notice the whole long field. And that's because DST actually is important information that you don't want to miss. And I'll show a whole table of how that is encoded. That's actually a nonlinear code that we came up with because of the different likelihood of different schedules of DST. Okay, now for the information encoding. So the time is represented as a minute counter in a century. So rather than speaking of what time is it, what hour is it, what minute is it, what month and what day, we count the minutes in a century, and there are 52.6 million of them. And that number can be represented by 26 bits, if you follow the math here on the third bullet. And these 26 bits are represented with a field of 31 bits using a linear block code with 5 parity bits. So there's some math behind that. This is well-known theory. And with this amount of parity bits, you have the correction capability of 1 bit, and you can even detect when 2 bits are erroneous. You cannot correct that, but you can detect that. And so you wouldn't think that it's some legitimate word that you're receiving. So it really helps to have that kind of redundancy in the information in a wireless communication link. And it's kind of an obvious thing that, Wi-Fi and cellular have, but as I said, 1965 mindset, so no redundancy. So I spoke about the synchronization word and the advanced notification for DST. And the radio controlled clock based on the new broadcast can have these 3 different modes of operation. Acquisition is when it first receives and just has no idea what time and what date it is, and then this SNR needs to be higher so that all the bits can be decoded correctly. And this will be noticeable to users, so we would like it to be short. We don't want to have to receive, 5 consecutive minutes and compare them to one another or whatever. We would like to do it quickly, but then there's this compromise. Tracking, on the other hand, is done kind of transparently. So if every night at 2 a.m. it receives that sync sequence and corrects that 0.3 seconds of drift that were experienced since the last time, it's something that the user will not even be aware of. And the SNR for that can be relatively low because it involves the correlation operation wherein you take the known sequence of 11 bits in this case, and you correlate that against what you're receiving in a window which is plus minus 4 seconds around where you're expecting it to be. We just chose 4 seconds because of the possibility of your crystal and your clock not being the best. But over the course of a day, it really shouldn't amount to 4 seconds. And then we did all the statistical analysis of what are the chances of you making an incorrect timing adjustment in that window versus the SNR. And I'll show some graphs of that. And then information reception or update has to do with that next DST transition or leap seconds, things like that. And then I don't think I should go into the details of this. The whole 6-minute sequence that I spoke of can appear in the signal if enabled. Sometimes it's enabled in the broadcast, sometimes not. Can appear in the broadcast twice in an hour, at 10 minutes after the hour and 40 minutes after the hour. Now, a big drawback to it is that when it appears, the regular frame doesn't appear. And the only product that is out there offered by Lacrosse can only receive the 1-minute frame. So actually, if you turn on such a clock and you were unlucky and it was during those 10 minutes, then you're going to have to wait for those 10 minutes to be over so that you'll be receiving the regular frames. But the idea in implementing these 6-minute frames was so that even in conditions of worse SNR, when you really only need the time and you don't need the date, and that Lacrosse clock doesn't even display the date, and nor do most analog clocks, then you're fine with something that can represent only 48 different possibilities when you think about it. 24 hours a day, twice in an hour, so there are only 48 different times. So each one of these was encoded differently in a sequence of 360 bits that are constructed as shown in this diagram. And we did the analysis and simulation and experiments, and that gained us another order of magnitude of SNR robustness. Here's the structure of the new receiver, the ES100, as we call that chip. So it has an analog front end, followed by an analog to digital converter. And then everything is in digital. There's no significant narrow filtering like the crystal that we saw in the analog legacy chips. We added a switch in front of the analog front end that allows us to select one of two antennas, and I'll discuss that. And so the amount of analog is quite minimal. And the entire demodulation effort and algorithms and all the steps are listed inside the block diagram are all in digital. Carrier recovery, synchronization, demodulation, decoding, control, the AGC, all in digital. Now, it's important to note that the antennas that are used, being a coil, an inductor, this is what they look like. And you're familiar with that. If you ever open one of these clocks, it also looks like the antennas in our AM receivers. They operate in parallel with a capacitor, together forming a parallel tank or like oscillation circuit. And they're known to have high impedance at the resonance circuit, I meant. So it doesn't oscillate. But the resonance is 1/2 pi LC, and that's when you get the highest impedance, and that highest impedance will be dictated by parasitic resistances in the coil, ideally infinity. In practice, some kilo ohms. So you don't want to load that and thereby DQ your tank and lose on the energy transfer from it. So the receiver needs to also have a high impedance, which really makes things difficult with testing, because all the equipment, like a spectrum analyzer is 50 ohm. So that was a bit of a pain to deal with that. The demodulation and operation are all based on software, as I said, with the detection being based on fast Fourier transform. And so everything is in this single chip, demonstrating over 20 dB of superiority over the legacy solution. And that's just in the 1 bit per second mode, not in the 6-minute sequence. So this is what a prototype receiver looked like based on a module with the ES100. The ES100 that you see in this photo, the square in the middle, is the first packaging that we supported. And then at some point, we no longer supported that because clock manufacturers wanted that cheap, die on board kind of solution. So it's only available in the form of die. And, there's that drop of glue on top of it. And those are the kind of, most of the modules, also from Universal Solder, unless he still has some of the old ones, are going to look like that. So this prototype receiver was based on an MSP430 that we programmed to communicate with our chip and display the time. And I carried it all over whenever I traveled and experimented with reception in various places. Notice that the antennas are positioned perpendicular to one another, such that if one of them is in the completely wrong orientation, being at a null, then the other one would be at maximum. In worst case, they would both be at 45 degrees away from the correct orientation, thereby losing only 3 dB. So not so bad. This is what the dye micrograph of the ES100 looks like. So interestingly, it has a huge area dedicated to memory, and not so much to everything else, with the analog portion being particularly small. So this is all in CMOS, 180 nanometer, manufactured by Tower, a fab that coincidentally is in my home country of Israel. I didn't choose it. We collaborated with a company by the name of Triune Systems at the time that helped us with some aspects of the design, like voltage regulators and things like that. And they were already working with that fab. So that's the history behind the choice of that particular process and fab. The reason why there's so much memory needed is because this clock operates not in real time in terms of the demodulation, but on recorded data. So first the data is digitized, stored in memory, then post-processed. And of course, the delay between the end of that processing and when the recording started is taken into account so that we end up displaying the correct time. Here is that single product available in the market based on the ES100, the lacrosse clock. So this image was taken just yesterday. I remember being able to order it for like $40-something. At some other points in time, it was $80. As of yesterday, $50 on Amazon. I guess it's a matter of demand. I can tell you the price of the chip didn't change. And on the right side, you see on the lacrosse website. So look at the difference. I mean, come on. First of all, you have to work hard to find it. You go to their website, you ask for atomic clocks, and it displays all these. And amongst these 8 clocks, there's this single one that is based on the new technology. It's not highlighted. They called the technology ultratomic. And one just wonders, oh, why is this one 97? Maybe because it has a better, stronger glass in the front, which, yeah, it does have strong glass. One of them has plastic. The plastic is actually more expensive. So, yeah. I don't know how much of this lacrosse sells, but Amazon apparently sells, because if you can see here, they've got a review average of 4.4. 2,000 people reviewed it, and 100 bought it in past month. I can see there. Okay. And when you read the reviews, the weaker reviews are because of something mechanical that users are not happy with. You typically find users expressing satisfaction with the reception robustness, with their experience being not so great with legacy clocks. This is where you can find the modules, Universal Solder, based in Canada. So that's www.universal-solder.ca. And here I show some examples of mistakes, of errors that clocks display. So this photo is one that I took some years ago, where we see the year 1992, Back to the Future. Of course, the year was not 1992, but as I show on the right, the numbers 9 and 8 in BCD are only 1 bit apart. And so that digit, oh, wait, let me think about that. So, that was supposed to be 2012. I guess I took that picture in 2012. So that 9 was supposed to be a 1, okay? The year 2012, so only 1 bit wrong. And notice that in the indicator of reception, that tower thing with the like RSSI sort of indication, you think, oh, I received just fine. You could believe what I'm saying. So the year is not so bad, because we're not going to get confused. But here is an example that I took a lot more recently, where DSD was messed up. It just missed the DSD and still showing robust reception. And on this particular clock, I have additional photos showing the minute wrong, the hour wrong, all for that same reason of the legacy broadcast protocol not being robust enough. Here's an experiment that I did at the time. This is over a decade ago with DSD transition. So, that comes that time, 2 a.m. Let's see my clocks turning back to 1 a.m. And so some of them did, but only at 1:03. It takes them time. They only start receiving at 2 a.m. typically. So for at least 3 minutes, you get the wrong time. And some adjusted around midnight. You get all kinds of results. I mean, all I'm asking for is for a clock to show the right time, right? I'm not asking for too much. The clock should be able to tell me the time and not me tell the clock. But my experience is, at least with my aunt's Jaguar, every time I would come to her, this was years ago now, she has a Honda. She'd say, "Oh, can you please fix the time in my car so I don't have to take it to the dealer?" I mean, imagine a Jaguar. It has all these bells and whistles and nice features, but the clock won't even tell you what time it is. You have to tell the clock what time it is, at least twice a year. So here's that table that I promised for representing the DST, the Daylight Saving Time code. So all these 6-bit codes were intended to represent when is daylight saving time going to take place. So currently, it takes place the first Sunday of November. And then on the second Sunday of March, we start DST, right? We come out of it the first Sunday of November. So those are the dates that Congress decided on in 2007. It used to be April and October. It moved to March and November. And they may change it again. And so I sat down with NIST and we decided on this potential schedule, a list of schedules that Congress, for whatever reason, may want to change again to. And one of the possibilities is that there won't be any DST at all. Anyway, so we looked at the options and what their likelihood is, and the coding was done accordingly such that the distance between codes is not the same. And that's why it's a nonlinear code. The block code that I spoke of before that is used for the representation of the minutes, going from 26 bits to 31 bits, places all numbers at equal distances from one another. That's called a Hamming distance in the world of coding. And so here, it's different distances, and there's that logic behind it. And a whole paper came out about that I published with Ying Si, that PhD student from SMU that I told you about. And now to those graphs for tracking that I had promised. So we did the whole analysis of what would be the probability of error in timing versus SNR when we look at that 11-bit sync word. So I'm not going to go into the details here, but just want to assure you that the analysis was done. And based on that, we decided what would be the right threshold for making a decision on acquisition. So if the receiver is not sure, that's like, I should try again next minute. After all, the acquisition sequence is available every minute at the beginning of the minute, the first 11 bits. And just some fun photos from reception trials before we had that prototype receiver that I showed you. Here's an even older one. And I put it in all different places that I traveled at, and airports and my aunt's basement. And airports are quite problematic in terms of the level of interference and the structure typically being such that there's great shielding losses. So we summarized all these results so that we can show investors, oh, look how great and how reliable our system is. And nobody else can design a receiver based on this broadcast format because we have the patents. So yeah, it was a great story to tell, which helped us raise funding. But the reality was that microwave oven manufacturers didn't necessarily care to incorporate it. Cars didn't care to necessarily incorporate it, and even clocks. We only see one clock with that. So not a big success overall from a commercial point of view. Now to the antenna issue and its orientation. Here's an experiment that we conducted where we placed a rod at a certain distance from, you see that T, that transmission antenna. I bought that from an amateur. It's a huge ferrite, and it's actually impedance matched to 50 ohms. So that antenna could be connected to 50 ohm signal generators, 50 ohm spectrum analyzer, and I still have it. If anybody is interested in it, I'll ship it to you. So just let me know at no cost. A 50 ohm, 60 kilohertz antenna. So in this experiment, you see we drew the angles around an antenna, and we rotated it and got unsurprisingly, this plot showing that you could be in a null, or you could get the reverse polarity, and it's a cosine. And so that's why you find in instructions of these radio-controlled clocks, not atomic clocks, they're supposed to be called radio-controlled clocks. If it doesn't work, put it on a different wall. But hey, I want it right on this wall where I can see when I'm eating breakfast. Nope, maybe that doesn't work well. You have to put it on the other wall. So in this clock, there are these two antennas inside, perpendicular to one another, and you can put it any which way. This shows the probability density function of a cosine. So when calculating based on that, this is the histogram that you get for a regular clock that has only one antenna. Let's look at that histogram for a moment. People don't realize that when they buy such product and put it on the wall. You have over 10% probability. Look at the rightmost bar. You have over 10% probability of experiencing over 15 dB of loss. That's 30x. 15 dB means you'll only get 3% of the power you could have. So 50% chances you're in the first 3 dB. That's not so bad. But then with probability over 10%, you could be losing between 3 to 6 dB. And you could read by yourselves what each bar height is, what the losses are, and the probability corresponding to it. So not so great. Now, when you have two antennas, look at this much better picture. With 60-degree probability, you'll only experience up to 1 dB loss. And between 1 and 2 dB, which is really negligible, the next 20%. And then with the next 25%, 2 to 3 dB, and that's it. That's the end of the story when you have two antennas. And if the second antenna happens to be 9 dB lower, and there's a reason why I assume that, still the picture is not so bad. And that is because it may be difficult to put in two rod antennas in a flat clock. So here, the antennas are on this wider bottom. You see when I'm aiming at the camera now. And the antenna is a few centimeters, not 6 or 10 like many that you find in some products. So it fits. But what if you want your clock to be really flat? So we actually developed an antenna, a loop antenna with a few turns, so no ferrite, so it doesn't have that enhancement. But we managed to arrive at a gain that was 9 dB lower, and here's the statistics for that. So not so bad. But that's not what's used in the lacrosse clock. The lacrosse clock has two tiny antennas that are actually perpendicular to one another inside the analog movement. So here's some study of how the MSF broadcast from the UK can interfere with a receiver on the East Coast. But this doesn't even take into account the possibility of the orientation of the antenna being favorable towards MSF rather than towards WWVB. When you take that into account, the possibility of like random orientation, this is how bad it may look. So the signal to jamming can worsen by as much as 10 to 30 dB. And so this is the situation that people on the East Coast are facing, where reception from MSF is potentially competing with reception from WWVB, especially when not oriented optimally. Okay, that's I've reached the 1 hour. These are some properties of the receiver. I'll just quickly go through this. The 140 dB in particular. So I experimented with the maximum signal level by actually measuring with an oscilloscope, Pico, the Pico scope, that USB-based oscilloscope that you can connect to a laptop. So I took a laptop out to where the antenna was at the station, just outdoors, and I was pretty much under it, or very close to it. And this is how much I measured. 0.1 volt RMS, 100. It can't possibly be stronger anywhere else. And the chip can tolerate that, okay? The chip can tolerate that. And then the weakest when considering the minimum SNR needed for reception, when using the long sequences, is 10 nanovolt RMS. And so when you do the 20 log ratio, because these are voltages, you need to do 20 log for it to be the ratio of powers, we get 14 orders of magnitude or 140 dB. And that's more than any consumer market receiver. You think, wait a second, GPS can receive very low signal levels. That's true, but not very strong signal levels because you're never very close to the satellites. And so this is really a wide dynamic range. I thought that you'd get a kick out of that too. So let's summarize. The reception robustness overall improved by over 3 orders of magnitude when considering the introduction of phase modulation, specifically binary phase shift keying, which is an antipodal scheme. I showed you how that significantly increased the distance in the signal space. And then there's the different representation of the information using linear code for the minute counter, those 5 bits of parity, using a nonlinear code for DST, using 11 bits for the tracking, things like that. And multiple trials validated the significant improvement, with reception trials successful even in South Brazil, as I pointed out, South America, Mexico, Canada, etc. Different reception modes are supported as opposed to legacy clocks where it always receives the whole frame, even when you just need to make very small adjustments in timing, and then it may actually show you the wrong time. And yeah, the higher link margin allows for reduced antennas. The 6 centimeter and 10 centimeter antennas that you find in some of those legacy clocks, they're pretty useless. So although they're large and supposedly can pick up a greater amplitude of signal, that's not really where the problem is. I showed you those nice colorful plots from SPAWAR, from the Navy, simulating the signal levels in distant locations. It's really the MMN that dominates. And so the signal to noise ratio does not improve when you're in that kind of environment and you're increasing the size of your antenna. But being able to deal with worse SNR, which is what we were able to demonstrate through the algorithms, through the digital processing, that is what makes it a lot more robust. So you could just put in a smaller antenna and save cost and save size. And of course, being fully digital, it can be easily integrated into other things. Our hope was that microcontrollers would just have that as an add-on, and if you have such microcontroller in a microwave oven or whatever appliance, then you have the time with just that external antenna. But our marketing was not very successful. And the company being based on engineers out of TI, such as myself, with the mindset of we are just chip designers, we don't do clocks, our customers are the clock. Well, that was a mistake, I would say, because only Lacrosse did it, and we were not successful in penetrating with other companies that did clocks. And so the result was that the company went under. I'm kind of trying to keep things alive. And so I pay out of pocket for the Everset website so that if anybody Googles it, they still find it. And they keep getting spam emails like, oh, let me help you improve your website, all these companies. And it's like, okay, I'm not necessarily trying to market it more. And so, yeah, it's still alive, and there's still some stock of chips in Hong Kong. The address and the contact information are on the website. And there are never any new customers. And once in a while, Kundo from Germany orders a few thousand chips to make a few more movements that are then shipped to Lacrosse. So that's the end of the story, the good and the bad. And I'm open to your questions.
Thank you so much, Oren. That's really amazing. All the different things you have to think about, especially the communications methods, the techniques that you're talking about. It's similar to some other methods that we're using in HAMSI to look at differentiating signals from one another. So it's kind of using a couple of people on this talk. Christina, KDA-OXT, could tell you a little bit more about their working with cautious arrays, and the same sort of theory about the distance between the signals. So very cool. Anybody out there have any questions for Oren? Feel free to go ahead and bring those up. And
hey, Oren, the fact that you work for TI explains why you used a 430 microprocessor. That's a very old chip. And by the way, would you autograph this for me?
Oh, yeah. I actually send such clocks as gifts to people. I didn't autograph them, but like the factory where we had our chips tested, I sent them one, and Test Spectrum in Austin, a very nice guy that helped me develop the program and helped debug things when the probe card wasn't working. I sent him one. So glad to see that you have one too. Is it working well for you?
It works perfectly, and I've had it for 4 or 5 years.
Glad to hear that. Where are you located?
I'm 5 miles from WWVB.
Oh, so I got to tell you something. I made the point that the signal strength there is very strong, but the receiver can deal with that. That's not something to take for granted. So, and one of my earlier visits there, I had a small clock about this size, like an alarm clock, based on the legacy broadcast, and it didn't work in my hotel room. In Fort Collins, it didn't work, and I'm like, it can't be that the signal is too weak or that there's too much interference. Let me put it inside the microwave oven that the hotel room has. I put it inside the microwave oven. Of course, I didn't turn on the microwave oven. And then it worked. So the microwave oven provided enough shielding. And you guys, understanding the modulation will be able to explain why. The AM of the legacy broadcast is not on-off keying. The high level is 50 times higher than the low level, or 17 dB. And the low level, so that's 50 kilowatts, 1 kilowatt. Well, that 1 kilowatt apparently was enough to saturate the receiver. So there's no envelope detection. There's no, there's no distinguishing between, there's no PWM happening. The envelope detection was happening, but not the PWM demodulation. Just interesting anecdote.
Just a side, Keith. When you're not speaking, please mute. We're getting feed through you.
I have a question.
Sure.
How do you mentioned several times the technology is patented. How do you feel about open source implementations of your receiver, independent ones?
I'm glad you brought that up because I forgot to mention something important. Since the company went under, no payments were made towards maintenance of the patents. They expired pretty quickly. And so nobody has to, even if they didn't, who would come after you, right? So, and we need to also understand what it means when something is patented. Mostly that you may have difficulties selling a product based on the IP if the owner of that IP cares. When you build something on your own and without the purpose of selling it, it's a different story. So anyway, no patents to worry about. I wonder if one could even find them when searching. But anyway, I provided a list of publications so you can get an idea of the level of IP and sophistication from those publications. But back to your question.
Well, that was my question. Would you mind if there was a independent third-party open source implementation of your receiver? You might get some more life out of your technology.
So what you're saying
there actually is one, at least
there is one already?
Yeah, someone has already developed an independent circuit.
Well, now I got to see how good it is and see if I can make it better.
Go back through the Time Nuts records. I remember at least one person implemented one. One thing, Oren, as you might remember, we bought a whole bunch of the lacrosse clocks at Dartmouth, and for the most part they worked electronically, but the hands fell off. We had a big problem with that.
Yeah, I've heard of such complaints about the mechanics. It's really unfortunate. I can tell you that the hands don't fall off of this one.
Yeah, exactly. That's why I'm really surprised that they haven't at least done at least one digital version. I
approached them at CES physically because they were not very responsive over emails. I met with Alan, the CEO of Lacrosse, And I said, Alan, what about a digital clock? I've been nagging you for years. And not very excited. He said there doesn't seem to be much of a demand. People don't really care.
Isn't until it's available.
They buy the cheaper junk. They complain if it doesn't work, but in most cases it does work because people live close enough to the station, and in wooden houses here in the US, houses are built for the most part, electromagnetically transparent. Those who live in apartments in large buildings, good luck to them.
They kind of forget about us in this backwater called New England.
So there isn't enough motivation, and nobody seems to care. And so this company in China, Karen, who developed this prototype, they weren't going to market it. They just developed it, and we didn't know how to market it. And so it never was marketed. And so you don't see anything digital based on the technology. And I think that it could have been successful.
I would love to have a radio-controlled clock where you had 2 UTC and then local time. I'd love to have something like that.
Oh, talk to MFJ about that. Oh, sorry, they're out of business.
Sorry. Yeah.
Well, with 2 clocks, so you can have 2 separate clocks and just set them to different time zones if they support that far of a time zone. Most clocks available in the US only support American time zones.
I think you'd have to move the hands. Take the hands and put them where they shouldn't be.
One could do that.
In a week or in a few weeks, Canada is shutting down CHU, and I'm not really familiar with it. But is it analogous to WWV? And does that represent a growing trend where in 2018 WWV didn't get funded almost, and so is that coming, or is there going to be one of these massive technology changes where existing technology will be useless because they see an opportunity to sell new clocks that do work? Are we in danger of losing legacy technology here again?
Okay, opinions. I have my opinion.
Well, remember, WWV is not WWVB. Radio controlled clocks do not use WWV unless you have one of the old Heathkit totally accurate clocks.
I mean, there's another possibility here that I've kicked around for a long time, which is that if you can't get these signals because they've gone off the air, build a local emulator. It wouldn't be hard.
Yes.
Generate very low power, 60 kilohertz. I mean, the reason I haven't done it so far is because I don't want to take the risk of QRMing the real signal. But if the real signal is no longer there, well, that problem goes away, and you can make all these clocks work again.
Well, that's not really a problem with WWVB because any transmitter you make is going to be very weak. It's not going to get to the next house.
I hope
Phil.
Yeah.
This is Paul, WBATSL. Done it, been running for 10 years.
Excellent.
The antenna's in the basement. I've measured the radiated power, and basically it doesn't get out of the basement, but it certainly takes care of my clocks quite nicely.
Oh, excellent.
Well, I've already had to do that with the internet radio when they bricked all my internet radios by turning off the server. So now I had to run the same software on a small unit that broadcasts through my Wi-Fi in order to keep listening on the bricked radios that somebody decided, they'll just buy another one. So
I love it. That kind of story is very satisfying to me. Somebody wants technological obsolescence and you fight back. I love it.
Okay, but that's just playing around and having fun with amateur stuff. To answer the question seriously, we have to realize that the times are changing, and when these broadcasts started out, they were very much needed and were unique in what they provided. Nowadays, there are so many sources of accurate timing available to us from various different channels, one of which is even cellular. There's GPS, although that's limited to outdoors. I mean, there are all these solutions, right? And in the NTP servers. And so it's somewhat justified for the government to say, hey, I'm not going to pump 50 kilowatts into the air 24/7 for a purpose that is really outdated. And so I was really concerned at the time when they spoke of not funding it, and I think that's going to come again. And so, yes, I do see what happened in Canada. as a trend. It's not that Canada is in some economical crisis that led to that. It just made sense. It made sense to have it in the past and makes sense to not have it now. And as much as we may be emotional about it and we have some history with it, it's like I saw people protesting in my hometown when some old cinema was taken down because a new mall had to be built. Oh, we remember going there as kids and all that. Yes, I remember going there as a kid. So what? Who cares? It's the town of Ra'anana, by the way. That's where I grew up in Israel. It's like, so I care, but it makes sense to build that new mall, and there's money making behind it. There's money losing behind having that old cinema compared to it. So it's similar. Wouldn't you
Well,
agree?
I did. Question. I did a quick internet search a couple days ago, trying to determine how many so-called atomic clocks are in operation in the United States, and I didn't have any luck trying to find the answer to that. Lacrosse probably has better marketing research than I do, but I'm guessing it's millions
Yeah,
of
it
those
is.
radio controlled clocks are out there. I've probably got 5 of them or 6 in my own house.
Right.
And so I guess I quarrel a little with the answer you got from the lacrosse person. I think there's been millions of those clocks sold, and if you could sell an even better one, now maybe what they're worried about, maybe the real question is it's going to cost twice as much as the ones that you can buy today, but you can still walk into a Walmart and buy those clocks. So uh, to me, they're a very successful consumer product, and I'm surprised people aren't in the market for even better ones.
No, you're right. You're right. WWVB is still useful, but I'm referring mostly to WWV. I mean,
Well,
Oren, let
yeah, I
me,
understand that. I was going back to the original question of why isn't there a market for the chip and for the new phase decoded versions? And to me, I guess I'll quarrel with the lacrosse guy that said there's no market, and I go, I think there's a huge market for it, and I
no,
think
there's
that market's been out there for 20 years, and still, I'm sure they're still selling those digital versions of the clocks. I personally don't want a foot tall analog clock hanging on my wall, but I'd sure buy a digital one that sit on a desk.
Christina, you had a comment I think you wanted to add to the argument of
yeah,
WWV. Go ahead. I'd like you to
yeah, I
get in there.
I want to push back on the notion that WWV doesn't have additional use because it does have scientific use. I'm dropping some links in the chat for those interested. Those are all papers using WWV as a scientific beacon. And then I've got one more for you guys that used CHU as a scientific beacon during the solar eclipse of 2024. So this has been a signal of opportunity. Both of these sets of stations have been signals of opportunity for HamSci since we got things started with this in about 2019. We're currently funded by the National Science Foundation through 2028 on the personal space weather stations, which got kicked off with this club at the WWV Centennial after we had a whole campaign of asking NIST to please, asking Congress to please hang on to the budget for WWV and WWVH. And although that campaign that we did get a lot of traction among radio types, my instinct on it is probably that we moved the needle, but I don't think we tipped the scale. I think that the main reason that WWV and WWVH were kept on the air is because they are a legacy system that ties into other legacy systems for resilient positioning, navigation, and timing. We have many ways of getting accurate time, and as consumers, we don't need to worry about it. But when it comes to the security and national defense concerns of having accurate time, you do want to have multiple layers. And so, I won't speak on it at any length because it's not my area, but I do know the Resilient PNT Foundation has put out a statement about CHU, about the value of keeping it on. They actually have a fairly long discussion about what CHU gives you that the other systems Canada is planning to switch back over to do not. And the, you know, it's a different set of things that let you get away from some of the pathologies of GPS. It's also that when GPS is the only game in town, it becomes a more sensitive target, not a less sensitive one. So that's also a reason to keep these going. On the science side, I do want to say this. We have about 40 stations monitoring CHU. I'm not talking about WWV and WVH, just looking at CHU's frequencies. We are having 40 stations collect their frequencies every day, all three of them, for scientific use. And since 2019, we have collected CHU signals. We have 25,000 observations as of like a couple of days ago, right? So those are all getting collected and put into the Personal Space Weather Station database. Now, the other thing that I want to point out is that for scientific purpose, CHU is not redundant to WWV, and WWV and WWVH are not redundant to each other. Because WWV and WWVH share the same carrier frequencies, there is an ambiguity about which one you are listening to, and you can use the sideband modulation to tell the difference sometimes. Detangling those turns out to be kind of an interesting problem. But we have a lot of data of those, and we have a lot of things people have been doing in that area. CHU, because it's the only one singing that tune at that time on that frequency, does not have that problem. CHU's frequencies also feather kind of nicely in with WWV's frequencies. So you have, you know, your 3.3, 5, 7, like it's much neater that way. Let me just take a quick moment here. I'm going to drop in a link to one of our data sets for people to take a quick look at. This was collected by Michael Howen, AC0G. His station collected this. This is his data from the day of the 2024 eclipse, which was April 8th, 2024. And if you look around 19 UTC, you can see this distinctive S curve associated with the eclipse. What that is that's basically the same thing you see every day, where there's a Doppler shift associated with the sunrise and the accordant ionospheric effect. And if you scroll down through the frequencies, you'll see the shape of that S curve change. So CHU has made this a much richer picture for us. The other thing that's going on is we've been collecting these data since 2019, which is the beginning of solar cycle 25. So we're about halfway through creating a record of that solar cycle, which is more than anybody's done before. So, you know, admittedly, we are using a public utility, right? A public utility that cannot be confined within a national border for a purpose for which it was not intended. That's what we mean when we say signal of opportunity. And it's not been in the charter of organizations like NIST necessarily to have this research angle, but that is sort of the direction they have gone. With NIST, you know, their mission has expanded from sort of the original thing of you're the guys that hang on to the kilogram and the meter stick to okay, we're gonna build the watt balance, right? Like we're gonna get everything connected down to a physical constant. Let's all do those things. So they are essentially a science organization at this point. When we talked to Walt Kopan, who was the last head of NIST under the first Trump administration, and he was saying, you know, I don't want to do metrification because I think it'll distract NIST from the science. So that's kind of like something they're doing. Now, I don't know that much about where a National Research Council falls on this. What I will tell you is that HAMSci has been preparing a board statement about this topic. We're going to be reaching out to them directly tomorrow, and I'll probably send something. Dave, I might send you something to disseminate to this list tomorrow afternoon, if that's all right. That'll be a statement. It'll be at hamsci.org/CHU or something like that. And you'll be able to see some of the statements that we have for why CHU, like WWV, like WWVH, is a non-redundant science resource. And we think that ideally it should be recognized and preserved as such. So kind of the same thing we were saying as when we were talking about WWV and WWVH back in 2018. but now we have a lot more data, and it has indeed been proving useful. These are very relevant for ionospheric ray tracing, for tracking the input of solar flares. And there's definitely stuff in these data we don't know about yet. This is good basic observational science. It costs very little. The impact is relatively high. And we're all going to be caring about it more and more as we have more and more low Earth satellites. So
the cost very little is what may be arguable, because if it was intended for certain applications and it served for them and they were considered critical, then that's already out. And one may argue, is it worthwhile keeping? I mean, I don't have an opinion. I'm just
there is embedded value in this. Sorry to step on you. We had this conversation back in 2018, so I only have the numbers for WWV. I've been trying to find them for CHU. For WWV and WWVH, we found that the budget amount for it was, I think, only $6 million a year, which is like a fraction of a penny per American tax-paying family per annum. It is an absolute rounding error. So, that's the American side. I don't know anything about the Canadians. I am hopeful that we will be able to have some sort of conversation about it. They obviously announced this and are moving forward with it very quickly. We do have plenty of Canadian members, Canadian signatories who are standing up for this, but there's not much time in which to do that. I'm sure they thought about what happened with WWV in 2018 when they made the decision to announce this in the way that they did, or rather didn't. But again, my hope is that we'll be able to get some more information and maybe have a conversation with the people making those decisions. And in any event, it's worth the ink to talk about why it's been a good thing for us. So
I'm reminded of how Oren was going to be brought back because of it, serving as an alternative PNT, but that's not happening, right?
Well, it was authorized, but somebody's been dragging their feet. And it would be a very good backup system. I was also going to mention that Oren could actually be used in the way we use WWVB.
Mm-hmm.
It's a very robust system, and Oren actually has time of day information embedded in it.
This is Paul, and I agree with you. I've been monitoring the Oren broadcasts from the western part of the United States in Boston, and they're very regularly here. I can hear them at night, double hop. And
oh, that's good. I have not been able to hear them, but
yeah,
you must have a better antenna than I.
I think so.
But that's good. I'm glad to hear that you can hear from this coast. We used to have people down in New Jersey, but those haven't been happening in a while.
Well, I do want to remind everybody we're looking at the clock. It's 7:35 here in Mountain time zone.
And he really means 7:35.
Well, I mean 1935. Excuse me.
I do have a couple of things very quickly, Oren.
Yeah, go ahead, David.
Of a radio nature. First is the idea that the two rods, but one of the antennas in some of these is actually vertical. How much actual horizontal polarized signal is there to WWVB? I presume it does get rotated some in propagation, but it is actually a vertically polarized signal, which requires a horizontal magnetic antenna.
Right. And so I was also wondering about that. I don't know the answer. Maybe Matt would have been able to answer that if he were here. But I did experiment with tilting a little bit and didn't see much of a difference. But when you're completely in the wrong polarization, you do see a difference. And it also depends on the environment that you're in. In some shielded environments, while you suffer great losses, you also suffer some kind of shift in polarization sometimes. So while outdoors, like in the desert, the polarization may be very similar to what it is in the station, there's I thought I experienced a twist, so to say, in polarization inside structure.
Well, a lot happens in the near field as well. And in fact, just an aside on that, I've got one of the universal solder units and one of the ultra atomic, lacrosse. The lacrosse is picking up in one of my labs. The lacrosse is picking up the signal, and the development system does not, even though I can get it fine elsewhere. So that's very curious that right next to one another, the two systems, even though they're using the same receiver chip, same antennas presumably, two
No, that's
different
a good experiment.
signal situations. We may talk about that.
Yeah,
One
yeah.
other thing is I noticed that Scott Newell asked about the long code, and I think I know the answer to this is that no, it hasn't been used because you did design a chip to receive it, but at last I heard from you, it hadn't even been implemented.
Fully tested, or yeah, so it wasn't really deployed. It was supposed to be an ES200,
Right.
which would cost a little more and would support that feature, and that never happened. But there was a lot of work that was put into it, so it was validated, at least from a theoretical and experimental point of view, just not productized.
And the coding is open source, so we could implement it ourselves, correct?
Oh, yeah, absolutely. And we can ask NIST to make sure that it's on. It may be on now. I kind of lost track. Sometimes I said, don't bother, turn it off. Oh, it is on. Okay, so every hour, twice an hour, at 10 minutes after and 40 minutes after, a whole 6 minutes of a long sequence for broadcast. And the reception of that should be quite robust.
This is Paul cracking up on that, Oren. You know how much trouble you caused me getting rid of that code?
Oh, you mean the phase modulation in general, not the 6 minutes.
No. Hang on. On the DPSK-er, everything was running good. Then they turned that on. So we did rewrote the code to take care of its behaviors.
But it's the same modulation, BPSK, during the 6 minutes and during regular 1 minute frames.
It changes. But we caught it, and then we were going like, "What's going on here?" Anyhow,
hey, I've got a couple of questions if we still have time.
Let me ask one more quick one.
Oh yeah, sure.
Is there going to be a way that I'd like to release this, or will somebody release this to Time Nuts, the recording? And I'm happy to release it, but I don't know where the link will be or anything.
Are you talking FMT nuts?
No, Time Nuts.
Time Nuts, yeah.
Okay. We'll put it up on the WWV Amateur Radio Club YouTube channel at some point here.
Okay, yeah, if you've got the link to that, if you could put it in the window, I'll grab it.
Off the top of my head, I don't have it.
I put my email in the chat because there were a few questions that were not answered, like specific details about the interface. Is it JTAG? Yes, it's JTAG, but feel free to connect with me on LinkedIn, send me emails. I'm a busy guy, but I'll want to support you. And maybe I'll recruit Volker to help with that because he became familiar with the chip and managed to design around it.
I just want to check and see, have we got any questions on chat that we haven't covered? Have you been watching that, Dave?
Yes. There's a few that, Oren was just saying that we might not have enough time to hit all those. I don't know.
Okay.
I want to go ahead and get David Gingold. Go ahead, David. You had a question.
Thank you. I'll do a moment of show and tell. I've had a sort of long-running project to build my own receiver for the BPSK signal. Here it is. You can see it on the camera. This is based on just a little ARM microcontroller you can get for $1.50 or something like this, an ARM chip that will run at 40 megahertz. And it's one of these system on the chip things, so it's got a lot of little peripherals built into it. So it's an ARM chip. It's got an A to D built into it. There's a couple of op amp chips and a variable gain amp on the board, and that's kind of it. And then I have a coil that I hand wound that sits in my little bag here. It kind of works. I did all the software myself. It was sort of an exercise in doing some signal processing stuff. I went down various rabbit holes of trying to make it work better. I'm on the East Coast, so it's a little bit challenging to receive stuff here. It's been fun. I get distracted with other things in my life, and then I come back to it once in a while. And maybe one of these days I'll open source it. I got a couple of technical questions for you, Oren. One, related to sort of how accurately one can receive the time with this. Is the propagation delay that you get between the transmitter and where we're receiving, is that stable? Does it vary over time? Does it vary by more than a cycle? Will it flip the phase?
Flipping the phase is not a problem,
right?
Because we look at things at a relative point of view. And as for what the delay is and what its impact is, it's on the order of milliseconds, well, depending on where you live. But our thought process was we're targeting consumer market kind of clocks. This is the kind of product we had in mind where it's not really a care about. In professional, P&T equipment, it may be, and there are all kinds of papers you could find out there about 1 microsecond level timing that people were able to achieve based on WWVB.
Okay, so you can actually do it pretty well. You can do it without slipping a cycle then, right? Oh, that's pretty cool. The extended low power format has this thing where it sends out a stream of bits, then it sends out the stream of bits in reverse, right? And there was some cryptic thing in the paper saying, well, that helps for some signal processing reasons. Can you give a little bit of an explanation of what the thinking is behind that? Is it just we're going to play the bits twice, and that way you get to try to see if you've got bit errors, or something more sophisticated?
No, I think it had to do with the shape of the autocorrelation. So, the whole timing works by correlating the incoming sequence with what you expect it to be. And I'm trying to remember what the logic was, but we found that was beneficial.
Okay, that's interesting.
And also simple to implement.
Yeah, I could see maybe it simplifies the implementation. How much memory do you have on the upper set chip?
I don't remember by now, but you saw the size in the dye micrograph, so it was quite a few. So I can tell you that we recorded, so we can calculate that right now. We recorded over 2 minutes of incoming signal.
Yeah.
Okay, something on the order, or we were able to record over 2, but we typically process over 1. But let's assume 2 minutes at 20 hertz of a sampling rate. So 20 times in a second.
Okay.
So you could calculate, and the number of bits, was it 10 or 12? So you can kind of get a rough estimate of how much RAM would be needed to store that much. Oh, but wait, that was just for that's for the shorter receptions. The 6 minute would require recordings that much longer. It's not a whole order of magnitude, 6 minutes.
Yeah, that's a lot.
And what I didn't present today was another idea that we had for extra long sequences that were going to be even more than 6 minutes. But that's theoretically possible, and to gain another order of magnitude in robustness, that once in a while, once a day, you would have that sequence, and so you would only have to identify that sequence to know the time of day. Think about that.
Right. There's a third coding that is a once a day coding. Was that implemented?
No.
Okay, that was never done.
Oh, so you did read about that.
I think that shows up in one of the papers. Yeah.
Yeah. Right.
Okay.
So that was the idea. That was not even implemented in the TCG and experimented with, whereas the 6 minute sequences were, and so we called them medium actually because of the longer.
Right.
We call them the medium sequences.
Another question I have: the sync sequence, I believe, and I think I worked this out, can appear in the time sequence as well during certain parts of the century.
The 11-bit sequence.
11-bit sequence can also show up. The same 11 bits can show up later in the time sequence at the right moments.
Oh, you mean coincidentally?
Coincidentally, right? But that makes it a little bit harder to do the framing.
Okay, so the idea with the framing was, as I pointed out before, is that you already have a certainty of plus minus 4 seconds. You're only in tracking mode when you're reasonably confident that you already know the timing.
Right.
And so within that window, there is no such concern.
Right. But when you're acquiring the first time, you get this ambiguity.
But the acquisition is a much more involved process where we don't just look at the 11 bits. So there's a lot of conditions that have to be satisfied for the clock to announce that it has acquired. So the acquisition
do you look over subsequent minutes and just see that the time advance, stuff like that?
We could, but we found that we didn't necessarily have to do that for high confidence. For example, the 31 bits that represent the minute, 26 bits with 5 bits of parity.
Yeah.
So if you receive that successfully, meaning the indication is that no errors in there, and then the subsequent words also make sense, like the DST. Then you could decide with high confidence, and one can do the statistical analysis that you have received successfully, even though you only spent a minute or two on the recording. But yeah, when in doubt, or there seems to be at least one error that you had to correct in the minute using the parity, then there's always the option of receiving more minutes and seeing that it makes sense. The worst thing that could happen, and so we definitely avoid that, is that you display the wrong time. So one thing that would never happen with an Everset-based clock is that you get the wrong time. It can only take longer to acquire in certain conditions, but you won't get the kind of examples that I showed with legacy clocks showing you wrong information.
Yeah, and it might, and obviously, if you hit the 6-minute interval, it can take more than 6 minutes to acquire.
If you're not capable of receiving that, right?
Right.
So, which the ES100 currently, is not doing. So that kind of introduces a delay if you're unlucky. That again is twice in an hour, after 10 minutes and after 40 minutes after the hour.
Okay, that's cool.
I have a comment if I can jump in here.
Yeah, please, Keith.
On mine, I just assume that there's 10 minutes twice an hour that I'm not going to get anything, and then it'll reacquire. It takes a little bit of time to reacquire after that.
Reacquire? Why is it reacquire?
Well, that's how I view it. It might be something else, but it just looks like I don't think it's the same as what you're talking about is reacquiring. If I start it up during those 10 minutes, nothing happens, and then there's a little bit of extra time before I actually see a time show up. So I don't worry about it because my local clock doesn't drift that much during that period of time, and once it gets set, I'm okay.
Of course. I mean, your clock doesn't drift over 24 hours. If you look at the kind of crystals that you have in the cheapest clocks on the order of 10 to 20 ppm, it's fractions of seconds in a normal day.
No, it isn't. No, it isn't. It's seconds.
It's full seconds?
Yeah. I have a radio controlled watch, and if it doesn't sync, it's a second off after a day.
Okay, 1 second after a day. So it's typically a fractions of a second. Some are with 5 ppm crystals. They're not that costly, and you could calculate how much drift you experience with 5 ppm. So the clock.
But what I like about this particular arrangement, though, as I have it, is it updates 20 times an hour. Who cares how much it drifts for the rest of the day? I'm getting that many. It's 18 to 20 updates per hour. And well, I love it though. I just love it.
Yeah.
Okay, it's just a thought.
Pretty power hungry.
From a practical point of view, your clock on the wall with seconds. I'm not talking about clocks that only display minutes. A digital clock that displays the seconds is perfectly satisfied with one reception per day. And that reception is best timed middle of the night when the atmospheric conditions are most favorable. And as I pointed out, if it has already acquired yesterday or last week, all those subsequent receptions can be of tracking nature, where it only turns on the receiver for a quarter of a minute to capture that 11-second sequence and adjust the timing based on it. And then once in a few months, it can open up to receive the whole frame and see if something surprising happened with the DST schedule or a leap second has been scheduled. That's it.
I will say I've been impressed that it will lock during the day in Greenland in the deep fringe. The only time it wouldn't lock when I was at the station was when our radar was running, because the modulator put out a lot of hash. It wasn't only this clock that had a problem with it, but without that running, middle of the day, it locked up within minutes.
And by the way, with that radar, it's not necessarily because the radar is an RF transmitter. The interference may have come from power supply.
Well, it was the modulator. It was a switching modulator with tremendous ground currents into things.
So the
They
interference
actually,
will-
when they dismantled the radar, they sent it to Arecibo, and I warned Angel, you may not want to use that.
this
Now it's a
reminds
moot
me-
point, but
Yeah.
they were
At-
thinking
at
of using that modulator.
At Extendwave, we had an office on the 10th floor of a building in Dallas. And, doing a lot of experiments there, we figured that there's something in the building causing it. And it was the elevator. Turns out there was some PWM in the motor of the elevator at 10 kilohertz with a harmonic at 60 kilohertz.
Yeah.
And so we managed to trace that to the elevator.
Yeah, in our lab, we have a big problem with a variable frequency drive to a roof fan. You never
There's
know
noise
where the
everywhere.
noise is going to come from.
It's pretty hard to escape.
Yeah, EMI at low frequency.
Yeah.
So as I wrote in
Oren,
the chat, I'm not sure if anybody noticed. I'm free. I'm available on email and happy to answer questions at oren.eliezer@gmail.com. So feel free to contact me, and I'll send you information and help you as much as I can.
I
Oren,
want to.
well, thank you so much for
Thanks,
your
Oren.
expertise tonight. It's been really incredible to hear, and I'm glad we got so many experts on this call too. It's really great to have so many people stick around
Yes.
and be able to ask important questions like that. So, thank you very much for giving the presentation.
It was a pleasure.
Yeah.
Thanks so much. Great talk.
Oh, I just wanted to say, at the tone, the time will be coordinated universal time. Thank you very much.
Here it comes. Well, thanks everybody for being here this evening, and we appreciate your attendance. If you're interested in finding out more about our WWV Amateur Radio Club, please look us up on the web. And again, you can also write to the club if there's any questions or you need any other information. So,
Dave, there was a question, and maybe people saw the answer as to the club YouTube website, where presumably if you have all the permissions that you'll post the video. And I put that in the chat, and I'll remind people it's also in the minutes from most of our meetings. Down at the bottom is kind of a catch-all. It shows you the address to the YouTube WWV Amateur Radio Club channel for
but our
past
minutes are not
meetings.
visible to everybody. That's one problem. So we'll.
I understand that. I'm saying to members can see
Yeah,
that.
members can see that,
And
yeah.
if you're not a member, we can certainly send you the link.
And I just put into the chat our actual web page for those of you who would like to join.
Yeah. Thank you, David, for doing that. All right. Well, I'm getting hungry. It's 8 o'clock here. I'm gonna go cook some dinner. Oren, thank you again so much for being here, and Keith, thank you for talking him into coming and sharing his expertise. And Oren, let us know if there's something else you wanted to share that you didn't get to, because we can get you back on here at some point in the future. That'd be great.
Sure.
Yeah.
Thank you very much.
Very fascinating. And I'm looking forward to a digital clock, but I'm not very encouraged from what I heard.
We didn't get to talk too much about CHU tonight. I was hoping that we would a little bit. And Christina, thank you for filling us in on the efforts of AMSI. And you're right on all of those things. It would be great if we could keep CHU and WWV and WWVH alive on the HF bands, because AMSI is definitely using it, and using it for a purpose not to really keep tabs at the time, but to keep a watch on the ionosphere and seeing how it goes up and down and changes.
Yeah.
It's hard to get a beacon that perfect. We're gonna have to
yeah.
If we lose it, we'll have to think of a backup. But it's so good at its job, and I want people to know that fact. So the statement will be officially out tomorrow. Excellent. Well, I'll make sure I get it to me, and I will make sure I get it up on our website as well. So will do. Thanks so much. All right. Well, I'm going to say goodnight to everybody, and I'm going to hit the end button, so you're all going to disappear in all one shot. So 7-3, everyone. Thank you.
Thank you again for the presentation.
Bye-bye.
Thank you.